All right, so on my reminders announcements, they're going to be less and less because we're almost to the end of the semester. So we have mastering tonight. After that, there's only 2 more masterings the rest of the semester. We'll do a for real individual quiz today. For real. I actually brought it. I checked twice. Yeah, there's this one and 2 more masterings. There's one last seminar tomorrow at 11 a.m. in here. Our 3rd exam is April 23rd, and then our final is like 5 or 6 days after that. Then we're done. Yeah, a little bit. So, because, again, trying to remind you as many times as you can, the final is cumulative, which means 108 and 109 cumulative. Maybe that wasn't clear before. It's a full year, because, right, the only way you know what's going on in 109 is because you know a bunch of stuff from 108. And so, as you're looking back through all the chapters we've done, it kind of compiles everything we've done in the entire year. Yes, ma'am. I do something similar. So the kind of on average, whatever your exam average is going into the final is where your ACS exam average comes out. It's like right now the class average is, for all of our exams, is like 82, 83. So I'll make it so the final has the same exam average as the class exam average. Because there's no good way to curve it. Like it's not a curved exam exactly, but I'll just move it so that it's equal. Yeah, Paul?
What should we be concerned about from 108? So I took 108
a while ago, yeah.
2 years ago.
So I would say, in general, I mean, it's stuff that you already know. Like 108 mostly covers molarity, right? It covers periodic trends, right? In terms of what's the most electronegative atom on the periodic table? Fluorine, done. You know periodic trends. In terms of thermodynamics, they only cover delta H in 108, but we've already covered H, S, and G, so you already know that same material. So a lot of stuff we do in 109, you already know from 108. It's just you know more than you knew before. So it'll be all right.
What's the percentage of the grade is the final? Like 20?
Let me double check for this class. It should be. It is 20%.
The exams are usually, they're 15%.
Mm-hmm. Yep.
Okay.
Yep. So altogether, your 3 exams are 45% of your grade, and then this is 20%. Then lab is 10%, homework's 15%, and the quizzes are 10%. So.
Before the final, we'll know our grade before the final. So.
Yeah, so either it's on mastering, and you can kind of see where you're at, points out points, or because it's also weighted on mastering, or just shoot me an email, and I can shoot you back what your current grade is.
Okay.
Either way. right, you ready to talk about some more electrochemistry? Because I am. Okay. So, when we looked at the table on Monday, which is impossible to see, but the table is in your book. The table only lists reduction half reactions. So where in my cell do reductions happen at? Anode or cathode? Yep. All the reactions are listed as though they're occurring at the cathode. Obviously, we don't want all of our, we have to have one of each, one anode, one cathode. So, when you need your reaction for the anode, don't change the sign. Just write it down. So our equation's already set up to take into account the fact that one's at the anode, one's at the cathode. That's what the subtraction is. We're getting the overall difference. So if you flip the sign, you've messed up your math. So you just write it down. So for example, let's say I have what's an easy one? Trying to do this off the top of my head. 2. I think that should work. Alright, so let's say this is my reaction. A few things we have to sort out. First, what element, or what ion, is being oxidized? The bromine or the iron? The bromine, how do we know it's the bromine? It's getting more positive, right? It's going from -1 to 0. How do you know that Br2 is 0? It has no charge, and that's its normal state. That's its natural elemental state. Alright, so our oxidation. So how many electrons do I need to complete this half reaction? 2, and where do I put them, as a product or a reactant? Good, okay. A few different ways you'd know that. Oxidations always have electrons as a product, or charge balance, right? Over here I have 2 minus, so over here I have to have 2 minus. Alright, so that means this guy must be the reduction. How do I know it's the reduction? Process of elimination, and or what's happened to the oxidation state? It has reduced. So the reduction has a reduction oxidation state. How many electrons do I need to go from 3 plus to 2 plus? 1 each, and I got 2 of them, so 2 electrons. Alright, so then I would go to my table. And you can't really see your table if I hold it like this. Alright, so which one did I use? I used this guy up here, right? Iron plus 3, and an electron, still fuzzy. makes iron plus 2. Maybe if I go like this. Oh, that's slightly better. Focus. Oh, now we're in business. All right, so iron plus 3 and an electron makes iron plus 2. Its E0 is 0.77. All right, so now I need the bromine one. So bromine is right here. A bromine liquid and 2 electrons makes 2 bromine ions. It's written in reverse. Do I need to do anything about that? No, definitely not. Just write it down. 1.09. All right. Which one equation, 1 with the bromine, equation 2 with the iron, is occurring at the cathode? Okay, this guy, right? Reductions are at the cathode. Means that's at the anode. So my E cell is cathode minus anode, which would be 0.77 minus 1.09. I have no idea what the answer is because I just picked 2 random numbers. 0.77 minus 1.09. What would be the units of this now? Volts. Is this going to be spontaneous as I've written it? No, it has a negative E cell, so it's no longer spontaneous. Which means I picked 2 bad things to combine together. Non-spontaneous. All right, we'll do a bunch more of those. Let's talk for a second, though, about this table. So oxidizing and reducing agents are the other things we talk about in terms of electrochemistry. That's not a good sentence. There we go. Oxidizing agents are species that can gain electrons. Reducing agents are species that supply electrons. So when we look at the table, right, it's a table of reductions. And so here we have at the very bottom the strongest reducing agents. So what do we know about lithium and potassium, calcium? What charge do they like to have? Right, positive, right? Positive 1, positive 2, which means they would like to give away their electrons. That's their preference, which makes them very good reducing agents because they want to supply electrons. So things like lithium, what else did I say? Potassium, calcium. Right? They're happy giving away their electrons, which makes them great reducing agents. So then if I look at oxidizing agents, oxidizing agents are species that can gain electrons. And so looking at my table, we have the strongest oxidizing agents at the very top. These are compounds that gain the electrons to make the final product. So I have F2. All right, so what else do I have? So the strength of the reducing agent, and vice versa, the strength of the oxidizing agent, is related to its E0 value. All right. So now, how can we use our knowledge of oxidizing, reduction, oxidizing agents, reducing agents, to talk about spontaneity, right? Because we just left a chapter talking all about spontaneity. So how can we use our knowledge now to talk about E0? All right, so what does the 0 tell me about the concentrations of everybody in solution? 1 molar. What does it tell me about the gas pressure? 1 atmosphere. What does it tell me what the temperature it's at? Okay. So what we're going to do is we're going to take a look at the sign of E0, assuming that everybody's 1 molar, 1 atmosphere, 25 degrees Celsius. All right, so we have our positive E, which tells us spontaneity, our negative E, which tells us non-spontaneous. So let's take a look at a few example reactions and see if we can figure out if the reaction is spontaneous as written, or we have to do something to it to force it to change it to be spontaneous. So let's say, for example, I have So I have iodine solid and bromine ions making iodine ions and bromine liquid. We'll look at the iodine half reaction first. Is this an oxidation or a reduction? Reduction. So if it's a reduction, where do I put the electrons? As a reactant or a product? Okay, and then how many do I need? 2. All right, so let's take a look at the bromine.
Are you always going to give us the charges?
You mean if it's an ion?
Yeah.
I would have to.
Okay.
Yeah. I have bromine ions becoming bromine liquid. Is that an oxidation or reduction? Oxidation. All right, so if it's an oxidation, where do I put the electrons? As a product or a reactant? Product, and how many do I need? 2. All right, can I recombine these equations as is? Or do I need to balance them anymore? I'm good, right? Because this one's mass balanced. I got 2 iodines making 2 I's. I got 2 Br's making 2 Br's. And the electrons would cancel back and forth. So we're good there. I would then go to my table and look up the potentials of each of these reactions. All right, so the bromine one is the one we just did. That's E0 equals 1.09. And then iodine, 0.54 volts. All right, is the iodine or the bromine occurring at the cathode? Okay. What's that turn out to be? Negative. So, is this a spontaneous reaction as written? No. How could I make this spontaneous? What could I do to my setup? Reverse it. So I don't change the numbers or the signs or anything, but what if I change it so that now it is What have I done to my reaction? Which half reaction now is going to occur at the cathode? Right, the bromine is now going to occur at the cathode. So if I do that, so I reverse the reaction, which means now the sign of the reaction has changed. So now it's spontaneous. All right, so now I have a spontaneous reaction, which means now we're ready to start talking about how E relates to my delta G. Right, because delta G was a measure of spontaneity in terms of joules, and here I'm measuring in volts. We can relate the two of them through this equation. The standard state Gibbs free energy is equal to minus NFE0. All right, we have this guy. All right, our Gibbs free energy at standard state. What have we used N to be before? Right, still the number of moles. F is our new constant. This is Faraday's constant. And it is equal to 9.648 times 10 to the fourth joules per mole volt. All right, so if we're thinking about delta G and E, these two in the middle, right, are constants. They won't affect the overall sign of it. If I have a delta G less than 0, is that spontaneous or non-spontaneous?
Spontaneous.
Okay. So if that is spontaneous, if this is a negative number, what must E then be to be also spontaneous? Good, that's what we decided earlier. So what we already know, delta G has to be less than 0, which is equal to the negative of the E cell, where E cell would be positive to be spontaneous, producing a voltage. Let me do a practice problem. Let's do a practice problem. Let's say I have this equation. I now have a redox reaction, and I need to find the Gibbs free energy for this reaction. What is the first thing I need to start doing in order to figure out anything? Yeah, I need to find E, so I need to break it apart, balance it, put it back together, find E0, and then find delta G. All right, so we'll do the lead because it's listed first. All right, lead plus 2 going to lead solid. Is that an oxidation or reduction? Reduction. How many electrons then do I need to put 2. I need 2 electrons. Okay, how about magnesium solid going to magnesium plus 2? Oxidation or reduction? Oxidation, so how many electrons do I need over here? Alright, do I have to do any other fiddling with these two half reactions to be able to recombine them? No. So then we're ready to go to our table. And we would find lead on the table. Let's see if I can find it real quick. There it is. So here I have lead plus 2 and 2 electrons making lead solid. That has a potential of negative 0.13. Then I need to find magnesium. Let's see here. There it is. All right, I got magnesium 2 plus and 2 electrons. Make a magnesium solid, and its value is negative 2.37. All right, is the lead occurring at the anode or the cathode? Cathode. All right, so my E0 is 2.24 volts. Is that a spontaneous as written reaction?
Yes.
Yes. All right, so now we're ready to find delta G. All right, so we just found E, so we can plug that in and F's a constant. The only thing we have left to talk about is N. So N, besides being the number of moles, it's specifically the number of moles of electrons, which is why if these two didn't balance out, you would have to adjust it to figure out exactly how many electrons overall would be needed, which is what my next example problem is. So we'll do one easy one, then one challenge. Okay, so now we're ready. We got negative 2 moles of electrons times our Faraday's constant, 9 point. The equation's negative N, so it's negative 2 moles.
And so why 2 moles? You just need 1.
I'll make you add them together.
Because when I combine the reactions, I use 2 electrons and make 2 electrons. So overall, 2 electrons have been used.
I see.
Right. 2 got pushed out, and the other guy got 2.
Yeah.
So it's not 4, definitely not adding them. And it can't be 1 because otherwise this equation wouldn't be balanced. So it has to be, we'll do another problem here in a minute, and maybe doing the second one will help. 10 to the 4th joules per mole volt. That's right. What are the units? Joules. Does that make sense with what we know about Gibbs free energy? Yes. Good. All right, why don't we do a more challenging problem then, and maybe it'll become more obvious how to do this. All right, let's say I have Okay, so I have this reaction. We need to do three things. First, we need to balance it in acid. Then we need to find A0. Then we need to find delta G. All right. Which would you like to start with? The nitrite or the tin? Sure. We'll go crazy. Start with the hard one. All right, so here I have NO3 minus going to NO. I'm going to leave off the states of matter for now just because they take up a lot of space. All right, looking at these two compounds, overall we see it's going -1 to 0, but that's not the only thing we're looking at, right? Because they wouldn't tell me enough about the electrons. We need to find which atom within the compound is changing oxidation states. So what do we know about oxygen and its oxidation state? It's always the same and it's always -2. So what is the overall oxidation states of all three of those oxygens? -6. If the whole thing is -1, what's the nitrogen? +5. Okay, let's look over here. What's the oxidation state of an oxygen by itself? If the whole thing is neutral, what's the nitrogen? So I've gone from +5 to +2. Is that an oxidation or a reduction? It's a reduction of how many? 3 electrons. So where do I put those 3 electrons? So I put them as a reactant or a product? Okay. So now that's half of the first half. So now we need to balance it in terms of acid. Right, because over here I have 3 oxygens, over here I have 1 oxygen. So in acid, what are the 2 things I can add that are allowed? H2O and H+. Do I need any water on this side? No. I definitely need some water over here. How many? I need 2 of them over here. So now I have 3 oxygens and 3 oxygens, 1 nitrogen, 1 nitrogen. What do I need to fix now? Yes, I need 4 H pluses over here. Do I need to do anything else to that half? No, that one looks good. Let's move on to the tin half. All right, so I have tin plus 2 going to tin plus 4. Is that an oxidation or reduction? Process of elimination. That should be the oxidation. Good. How many electrons do I need then over here? 2. Do I need to do anything else crazy with my waters, protons, things like that? No. Can I recombine them right this second and call it good? No. Right, because the electrons would not cancel out. So what do I need to do to my top reaction to get it to cancel out? Okay, then what about this guy? 3. All right. So now I will have 2 of these. 4 of those. And 3 of these. But I just mistake. Should have been 8. Just like I forgot these guys. That should be 4. Yep. All right, so now we're ready to go back and find our E zeros. So that's the balanced equation. Good. We then need to go back and find our reductions and oxidation potentials. I have to pick compounds that are on the table, so you just have to trust me. I think tin's on the table. Tin. There it is. All right, so All right, so 10's right here on the table. I got 10 plus 2 and 2 electrons makes, oh, so that's not the right one. Let me find the other 10. There it is. 10 plus 4 and 2 electrons makes 10 plus 2. But in my new balanced equation, I have 3 10s and 3 10s. Do I need to do anything to the E0s? True question. No, don't do anything to the E0. Doesn't matter if multiplying by 3. E0 is still 0.15 volts. So, you don't change the sign, and you don't multiply them by anything crazy. You just write them down. Nope. A mistake. A mistake would change it. So don't do that. All right, so now we're ready to find E0. All right, so it's going to be 0.96 minus 0.15. That should be 0.81, is that right? Is that spontaneous as written? Yes. Now we're ready for this. So how many moles of electrons did I need to be able to combine those two reactions? 6. So even though we don't actually use this full balanced equation for any purpose, if you had not come back up here, broken into 2 halves, you wouldn't have the right number of electrons to plug in here. So it seems like a silly step, like I don't know why I'm doing it because you didn't actually need it. You'd have the wrong number of moles of electrons in that step. Ran out of space, 0.81 volts. Poor spacing there. Times 9.648 times. Oh, joules. I was making a check mark. I was like, yes, I'm right. But then it looks like a V. I forgot my joules. I'm so excited. All right, so we'll stop there. We'll talk about how we can then add in our favorite letter of the alphabet, K. So now we have G. We'll talk about K, which then means we'll lead up to Q. So we'll do some quizzing instead. We'll take a break and do a quiz.